Okay, so let's now solve it together, right? So let's take the first case when you have a point which is distance x and x is greater than r. So we'll take the first case, scenario A, when x is greater than r. Now let me just draw this sphere here separately, and I'll make it slightly smaller so I can draw it neatly. So let's say this is my sphere, right? And this is r, and I want the distance at a point. So I want the field at a point which is distance x from the center of the sphere. Now, first question I'll ask again is that what is the direction of electric field going to be? Right? So now, since it is about this axis, everything is symmetric, right? The field cannot be in this direction or in this direction. That's not possible. Why? Because why would it be in this direction? Everything is about this line, everything is the same. So it will have to be along this direction. So now we know that by symmetry, electric field will have this direction. Okay. So we'll say by symmetry, right? Electric field direction, right, would be along the radius or the radial line, right? Radial line. You can see that if I draw a line along the radius, it will be along the same direction. Now what I'll do is very simple. Now I'll just draw a spherical Gaussian surface, right? I'll imagine a sphere, right, which is of radius x. So this radius is x, right? This is x, and now I'm going to just apply Gauss's law on this. So let's do that. So we'll say integral E dot ds, right, is going to be equal to q internal upon epsilon naught. Right? Now at each point, if I take a small surface ds here, E, the direction of E is electric field is along the radial line, and the area vector also will have the same direction. If I take a point here, same thing. Area vector will have this direction. Electric field also will have the same direction. So basically, angle between the two is going to be 0, right? So if I take this element, I can write that integral E dot ds is nothing but E ds into cos of 0, which is nothing but 1. So this is equal to E ds, and therefore I can say now this is equal to integral E dot ds, and E is constant. Again by symmetry, if I take this point, since it is all symmetrical, this point will have the same electric field as this point. But obviously direction is different, but it will have the same magnitude. So I can take E as a common coefficient, I'll take it outside. So I can say this is equal to E into integral ds. And what is integral ds? This is going to be the total surface area. What is total surface area for a sphere? It is 4 pi into square of radius. So this would be equal to E into 4 pi x square, right? And this is going to be equal to q internal upon epsilon. What's the q internal? This whole charge is inside, right? So this is going to nothing but q, total q upon epsilon naught, right? And therefore now I can say that E is equal to q upon 4 pi epsilon naught x square, right? As you see, this is nothing but Coulomb's law. Provide Coulomb's law for a point charge which is at a distance x from the point you are looking at. So essentially, outside of this whole charge will behave like as if the field outside will be the same as if this whole sphere was just a point charge, right? So this is how we calculate for the electric field for any point outside the sphere. Now let's take the second case, which will be easier. Second case is when we are looking at inside. Exact same logic, nothing changes, same symmetry. I'll say that integral E dot ds, right, would be equal to q internal upon epsilon naught. Now what is E dot ds? Same logic. If I take a point inside, if I take a Gaussian surface, so I want to find, let's say, a distance r. I want the field at a distance, let us say r, right? This is my r, right? So I'll take a sphere of radius r, small r, right? This is small r, and again same logic. By symmetry, E and ds will be always along the same direction, and E is going to be the same at every point. So I can say this is equal to, exact same logic, this would be E into integral ds, right, which will be equal to q internal upon epsilon. Now what is q internal? the charge inside this is going to be 0 because it's all along the spherical conducting sphere. It's a shell, right? Remember, this is a shell, right? It's a shell. This charge is only on the surface, right? So now we can say E dot ds is equal to 0, right, upon epsilon naught, which is nothing but 0. So, and what is ds? ds is going to be 4 pi small r square. So E into 4 pi small r square is equal to 0, which means my E is going to be equal to 0, right? So very simple conclusion. So if you have a conducting sphere, right, uniformly charged conducting sphere, but it's a shell, right, conducting shell, let's call it, then field outside is going to be E equals q upon 4 pi epsilon naught q square, and inside it's going to be 0. Thank you.